So I'm Ron Noonan, product manager. I work with NFV solutions here at SUSE. And today I'm going to talk about, we're going to go through NFV, but we're going to get there by talking about OpenFlow, SDN, and NFV, what problems they solved, what they do, kind of a high-level look at what the market really was and how it formed, and then what the market's doing about solving the problem for NFV and the telcos in that market, and where interoperability exists and where it doesn't, and ultimately what SUSE is working on and how we are helping in that market. So we're going to go through it that way. So the agenda is we'll talk about NFV. We'll say what is it, what problems it solves, how does it differ from SDN, software-defined networking, and then OPNFV, the project direction, and what we're working on, just what we talked about first slide. So what is NFV? NFV is what this says, and it's network function virtualization. It reduces the deployment operating costs. You can read it. It's interesting, but what does it mean? Do people even really know what it means? Just distill it down to a few things. It reduces the deployment and operating costs, increases manageability. That isn't that specific. But what is interesting about NFV is it decouples the network functions from the hardware that they ran on before. And that's the real point of NFV. But we'll talk about what it really solved and how it came out to be. So I hear this a lot. Why is NFV different than SDN? What is SDN? Is SDN NFV? Is NFV just a different version of SDN? And it's not. Are they the same functions? What problem does NFV solve if it's not the same that SDN wasn't solving? And ultimately, are they complementary or competitive? What is it? And so we'll go through and look at that, talk about it. OpenFlow, SDN, so this is where the problem was. Ultimately, or originally I should say, that's kind of the way a network looked for an enterprise or a university in a normal layout. You get a multi-protocol network. You have lots of specific devices that handle the various types of traffic and implement things. It's not designed to be legible. It's just designed to look busy. The point is that you had a lot to control. And originally, there was no way to control everything other than if you had to implement a new network protocol on your network, you had to go out and touch every device that was responsible for handling the new types of traffic. And it was a very difficult thing to do in a very hard to manage environment. And there were no standard abstractions to handle how to deal with it. Every hardware device was its own managed environment. So really this was a complex problem. It mostly originally existed and was intended to be solved at the university level, but it quickly went into the enterprise level. The real problem was the lack of agility. The solution was OpenFlow. OpenFlow was the original protocol that was, well, I'm not sure if there weren't things before it, but OpenFlow was the protocol that was used and defined to help solve this problem. It was a standard protocol. It defined this, well, it even had an architectural concept to it of a network controller and a protocol. But essentially what it allowed you to do was have the ability that all devices would be able to answer to OpenFlow, and you could take a controller and manage them centrally. So the point was here is that you had an environment where it was very complex to manage originally, and you'd put OpenFlow in place, or the OpenFlow architecture with the protocol and the controllers in place, and you would have a centralized way to deal with managing the network. And that's what that was. And this quickly became called SDN, but they're not necessarily the same thing. People waving at the back of the room. It's okay. Software-defined networking, I'm just going to go through this quickly, but software-defined networking is an umbrella term. It encompasses what OpenFlow solved, OpenFlow being the protocol and this controller concept so you could centrally manage all your hardware devices. And it has these concept or technical terms, or I guess they're technical terms, upstream API, downstream API, control plane, data plane, all part of it. But really what it is a way for you to centralize and control everything. The problem was decentralized hardware. The solution is centralized control of decentralized hardware. OpenFlow did that. Software-defined networking grew out of that. It's not necessary. So I talk to different people, and I hear this often. SDN is the architecture, OpenFlow is the protocol. Originally, some people said OpenFlow was the architecture and the protocol. SDN grew out of it and then started to define a lot more. OpenFlow is the open APR with the simple architecture. SDN is the software-defined networking that you can do a lot more with. And this is where it gets interesting, because ultimately SDN, not everyone agrees on what it is. SDN is implemented by different people in different ways. You can do lots of different things with SDN. You can centrally control different aspects of hardware with SDN. But every implementation can vary. Every implementation by a vendor might be a little different than another vendor's. Where they all standardize is at the OpenFlow level. The other place they standardize is on some of these open source projects. When you look at an open source project like Open Daylight, that is an open source project that defines a software-defined networking architecture, and you can implement it along these lines. There are several out there. The real important thing that happens in this architecture, though, is that it gives you a way to actually control that centralized behavior of those hardware devices. It supplies a network controller that you can program and manage the devices. It gives you the concepts of network applications, orchestration, services, so you can do service chaining and tell things how to behave. You might say, when someone comes into the network, they have to talk to the firewall first, and after they talk to the firewall, they might have to follow a different rule to a specific location depending on what the firewall said. Or in an example yesterday, if it wasn't a good packet and they didn't like it, they might send it off for deep packet inspection. Different things can happen, and these are the things that you can define in the architecture. But what the architecture doesn't define is what are the devices being managed. So it's a nice architecture, this is an interesting point, that lets you have a controller environment, a centralized managed environment, the concept of things to manage and how to manage them and the things you can do and how the network should behave that you can program and reprogram. But it does not tell you what the devices on your network have to be. They can still be the same hardware-based devices as long as they were upgraded and modified so they can react and handle and be managed by this OpenFlow style protocol. Does that make sense? Okay. So what is network function virtualization? I mean, SDN just gave us a nice architecture, lets us manage everything centrally, lets us do everything that really needs to be done that the enterprise and the universities had a problem with. Well, let's look at this. I laugh at this, by the way, a little bit. NFVs came to market and they said, our job is to reduce CapEx and OpEx and be agile and flexible. And you look at the SDN mission statement, it's to reduce CapEx and OpEx and be agile and flexible. But they are different. They just have a similar sounding thing. Oversimplification, NFV grew out of the carrier needs to encompass hardware from multiple vendors. And that's the real difference right there. SDN provides the control and the logic for everything to behave and how it behaves and gives you a way to control all of the devices. NFV says the devices are a problem themselves. We need the devices to operate as software. We need to virtualize the devices. And that's the fundamental difference right there in the problem statement. The architecture is quite different. NFV replaces physical devices with virtualized software. Does that make sense to everyone? Is there a question as why would you do that? No questions?
Why would you do that?
All right. So, I mean, and this is interesting in that, you know, the motivations. Enterprise world operated with SDN and OpenFlow for a long time before NFV came along. And the enterprise world was not asking for NFV. They were not trying to change the hardware devices. What changed in the market was really from a telco standpoint and or the really large carriers that had enormous networks with enormous number of devices. And then as the world is evolving and the protocols that we use all the time are changing at an accelerated rate, and we have to keep those giant networks keep having to be updated. If they have to roll out new hardware every time a major change happens from 4G to LTE or something like that, just anything that drives hardware changes or hardware touches, it becomes a problem. And the pace of change is what is becoming a problem. And so the network carriers and anyone that has a really large network of devices that is being impacted like that, we often say this is telco specific. It could be any company that has the kind of behavior of a telco. I would imagine, I haven't talked to them directly, but I would imagine cable companies have the same problem. They're carrying a lot of the same kind of traffic. They have a lot of the same kind of things they have to deal with, and they're dealing with newer and changing protocols all the time. And so they have this problem of needing to touch hardware. NFV is the ability to virtualize all of this hardware. So it's also appealing that it reduces vendor locking because they're looking for interoperability. I probably skipped something here. So OPNFV, I didn't define that. Open Platform Network Function Virtualization is the equivalent in NFV to what Open Daylight did for SDN. It is a reference architecture on how you can put everything together to supply and build out interoperable virtual network functions that replace the hardware that handled those things before. Does that make sense? Okay. They like the interoperable because it allows things to be transportable, and it also reduces vendor lock-in. This did not come out that well on this projector. That is a standard reference architecture that you would see with NFV. You see this picture all the time. If you go to OPNFV, you will see this picture. If you go to a lot of vendors that supply NFV components, you'll see a picture that looks just like this. And what this picture really is a core architecture that has the ability to touch the physical network and then connect it with the virtual network. And it's got a core infrastructure where everything runs. Very OpenStack centric in the open model. And it's got an ability to manage that core infrastructure, and that's defined as a function. The other thing it has defined is the concept of virtualized network functions. And those virtualized network functions might be things like firewalls, load balancers. They might be router switches, and the like. Anything that you want to virtualize in the network will run as a VNF. And it's just a standard application. And by the way, a VNF it might be a standalone VNF, or it might be a distributed set of services that represent the VNF. It is a defined layer that runs on this virtualized environment and then is managed by an orchestration layer and a management layer that's defined in the architecture. This is where it gets interesting. So we'll go through this because it defines a little bit about where SUSE is applying its effort to help this market succeed. And it also talks a little about how the market is evolving. When we look at the core components, there's a different layout of the same thing. That piece right there in the middle is in fact that core, well, it's that green box on the bottom left is now the middle piece right there. The top part has orchestration and virtual network functions as two kind of grayed out boxes. When we look at that core architecture and we look at it from a open NFV standpoint, the open source or the open platform reference environment that uses open source software to solve all of these problems, you have OpenStack, KVM, Ceph, and then on the right you have Open Daylight, Open Contrail, ONOS, and the like. OpenStack is really what everything runs through in this particular architecture. And it uses Open Daylight, if you notice, we defined that earlier as an architecture for SDN. This architecture uses SDN and that style architecture, that open source style of architecture, to supply the network controller kind of flexibility into this market. So this architecture does a few things. It supplies an architecture for how to write and supply VNFs, virtualized network functions, and then how to run them on standardized open source infrastructure. So it uses KVM, virtualized storage, OpenStack, and then one of a few controller options. And this is where it gets a little muddy. Everything in this architecture, every NFV environment, pretty much you're going to find an OpenStack implementation. You'll always see KVM. You probably always see Ceph. You will likely see one of these in the solution, because each one of those is a competing project that supplies a network controller in a SDN format. And you could use any one of them, and the architecture does not define which one you have to use. The other thing that's in that architecture was the management and orchestration layer. Today in this market, the management and orchestration layer is defined, but there are several competing projects on how to complete this layer. The interoperability for OpenStack is clear. The interoperability for the virtualized environment for storage and KVM is clear. The network controllers are pretty easy to solve with one of the three. The management and orchestration layer is actually kind of a free-for-all. It's a little bit of the wild, wild west. You will see proprietary implementations that people write over the top that work perfectly well. You will see OpenO out there as an open source project to solve this problem. You will see OSM as a competing open source project to solve the same exact problem. You will see other open source vendors solving this on their own. And then you will see from very, very large network carriers writing their own solution here because they think they know how to do it just fine and they're writing their own. All of them are valid. The interesting thing about this architecture and the useful thing about this architecture is no matter which solution you pick at the top to do the management and which network controller you decide to use within the architecture, everything else is still interchangeable and the virtual network functions should still be interchangeable. So you still can build out a completely functional virtualized network environment with NFV and OPNFV, and you have some choices along the way. The farther you get out to the edge, the more choices you have, and the closer in you get to the core architecture, the more standardized it is. How to say that any better? So this helps direct where we're going to talk next, which is where is SUSE working to help this architecture succeed? What are we doing in this market? What are we doing with open platform NFV? We are, as a company, we are concentrating on the core architecture. We are concentrating on making the core components of NFV, OpenStack, KVM, the components in there, and then Open Daylight to start with, the pieces, and tailor those pieces to be used in a network function virtualized environment. Sounds pretty simple. SUSE makes OpenStack. SUSE makes Ceph. SUSE has a KVM offering. We are packaging up Open Daylight today. It's an open source offering. Seems pretty simple. But there's a bunch of details in here that are important. The virtualized environment by itself and the way it was running a year or two ago is too slow to handle network functions. When you virtualize an environment, you put a lot of overhead in there. If you're going to take hardware pieces that were ASIC-based kind of high-speed, high-performance devices and then take those functions and push them into a virtual machine, you can imagine just the overhead of a virtual machine is going to put a lot of latency into that picture. So there have been a huge number of modifications within each of these projects. OpenStack has some variations. All of these pieces have variations. The Open vSwitch has some major variations. And then you get down to the things like DPDK, which it's an acronym, Data Plane Development Kit. Intel originally built it and then turned it over to the open source world, and now it really is community driven and it's moving quite quickly. Those things have been modified greatly. And what they do is they allow this architecture to take advantage, or virtualized functions to take advantage of direct access to hardware in certain circumstances and bypass lots of the overhead that are normally associated with a virtualized environment. I'll just give you an example. So the DPDK. Normally, if I wanted to send a packet to a network device, I would send it, it would get to the network device, and it would interpret it. And in an open OPNFV environment, if that was a virtualized network function, I would send that packet, it would get to some piece of hardware, and then that piece of hardware would pass it into an operating system. The operating system would interpret that packet, decide where it's supposed to go, route it to whatever virtual machine needed it, and then that virtual machine would process it and send it back down, and you get this up and down stack kind of activity through the network layer. With DPDK, the Data Plane Development Kit, and the modifications of this environment, you can literally have hardware NICs that are aware of where things go, so that when that packet comes to the hardware NIC, instead of having to be passed in to the operating system to be interpreted, the hardware NIC can make the decision and send it to the right place immediately. It bypasses a lot of functions. So it speeds things up. And the point here is that this is an environment to allow network functions to run as if they were native hardware. That's what this architecture is for. Where we are putting our work as SUSE is in helping harden, make this core architecture hardened so it's carrier grade. We always like to use the term enterprise grade. And in the network world, they like to have a higher standard of fault tolerance, so they came up with the term carrier grade. Ultimately, it's the same thing. It's just a further process of hardening the components so that they have really high uptime and great hard HA, really. And also then the modifications to the components in the stack to allow very, very high performance so that you can take advantage. And these components are being modified continuously to improve the throughput that you can have in a virtualized environment. And that's happening. It's really working quite well. So all of these pieces that we're working on, we're tailoring for this specific implementation. And we will take all of that and then package it up and put it out on the Pharos Labs. Now the Pharos Labs is a little bit jargon. In the world of OPNFV, this whole architecture is in fact a multi-vendor architecture. Nobody typically makes everything. And if someone does make everything, they probably don't make it the best that someone else could make. The real goal here is this is an architecture, because it's got interoperability built into it, that you can take things and put them together and build out your implementation for a virtualized network environment by following this architecture. It's an implementation architecture, not a product. Each one of the things inside could be a product. Each one of those things on the edge could be a product. But because of the nature of this architecture being so big, I mean, OpenStack by itself is big. Open Daylight by itself is big. Ceph is big. Having to put all of these things together to try to figure out how you wanted to put it together and test interoperability is very difficult. So the OPNFV project or world has defined a set of labs around the world, or using the Pharos Labs around the world. And a lot of vendors and or places are hosting Pharos Labs. And the point here is that we can take these components. So when SUSE builds out and wants to distribute these pieces, we can take them and put them out on the Pharos Labs, all packaged up, implement them, and then start interacting with the other pieces that are on the edges, the different orchestration layers, the different management layers. We could even plug in different network controllers. And you can test and or try out different ways of building out this architecture. Because there is not one way to do it. There are several because of the edge pieces being variables. The core pieces are pretty fixed. The edges are pretty variable. Pharos Labs is where we will take everything, put it out there, and allow it to be tested. So actually, that is what SUSE is doing. This is what we are doing today. We are taking each one of these components. We have a team working on this and the various components. We're putting in the high-speed Open vSwitch. We put in DPDK. We have packaged up Open Daylight into the system. We're modifying the components so that you get the throughput required for the environment, and we're going to package it up and put it on the Pharos Labs so that then you can actually go out there and test in a public environment the interoperability and the virtualized functions that you care about running on the network. It's a technical thing. At that point, if someone decides they like an implementation, then we can take that implementation and put it into a real environment. A lot of blank looks. But that's what we wanted to talk about. That is just, well, this is the stuff that was, this is the Brahmaputra picture, which is the B release of the OpenNFV architecture. it keeps enhancing. There's a new release coming out, or maybe it's out, I forget. It's out. So the D release is being looked at. And there's also competition now down here. ODP is something we'll be working on pretty soon to add performance capabilities. But Cisco obviously knows how to do routers. They know how to do packet routing very well. They donated their VPP, vector packet processing, to the community, and we will be putting that into here, and that should speed this up even further. So we'll be continuously adding components into this architecture and down underneath and inside those components to allow it to be higher and higher performance, more and more like the ASIC-based environment that it is designed to replace. And then all of those pieces will show up on the Faro slabs as we move forward. Yes?
Are you doing anything with KVM?
We are looking at KVM modifications right now. If you want to address that, you can. But so I'm going to point at somebody here. Rosella is in the audience, and she leads the engineering team that's doing the work. Right now, the KVM we were using is the standard KVM that we have. But we are looking at things that we can modify in there, and there's stuff that will be modified over time. Yeah, so we have a real-time kernel that we can put into this too. And so that's an interesting topic. Do you have real-time kernel needs, or do you think that would help your environment?
Oh, sure.
Yeah, so let me describe that just a little bit. When you run they did some tests on this, and yesterday in the engineering demonstration, they went through and they ran an example where they ran it through a bunch of functions through OpenV switch, and they show the response times, and then they enabled the DPDK in OpenV switch so they could bypass a lot of the overhead that's normally associated, and they ran it again, and they showed it was 4 to 6 times faster. And you saw numbers, if I remember right, you saw numbers, I saw response times on one of them. Let's just say I think it was around 60 millisecond response times on some of the things, just in the example. And that's on a regular kernel. And the response times vary a little bit as you go each packet. When you put a real-time kernel in there, what you might do, well, actually, let me step back. On a regular kernel, you do that, you could draw a line across that and graph those numbers out and draw a line across on the average speed that they were doing. And you would get some variance on how those responses came back. And that variance might, it might be between 60 on average, but some of them might be 80. And every now and then you might have 100 or 110, depending on what's going on the machine and the environment. When you put the real-time kernel in there, it will handle those things very differently, and it will change how it processes the interaction and the I guess it's more of a polling environment. But what happens is you will see, instead of, say, a 60 average, you might see a 65 or a 70 average. The average will slow down a little bit because of the way it's actually managing the data. But that variance will just narrow down right to that number. And the point is, a lot of people find a regular kernel better for virtualized functions because on average, things are faster. And if every now and then something's slow, well, that's okay, if it just happens on occasion. But if you're running a function like radio or something like that, where if you have a lag on any type of response, you drop the connection, you want a real-time kernel. So real-time kernels are, I look at them as, yes, they're there and you can use them, but they're for specialized use if you need them. But on average, the regular kernel solves most of the network function problems. Does that make sense? Okay. Any other questions on network function virtualization? What SUSE is working on? Any other components to talk to? VXLAN? No.
It's an encapsulation, so I mean it's used. You can configure it for OpenStack to handle the tunneling.
I don't think it's anything different than what's there, right?
No.
Yeah. So the question was, is VXLAN being used, or It's in the environment. It's one of the components, and it is used as it sits in the component today. These are enormous architectures. You could ask about specific pieces in a component and go right over my head. But there's people in the audience that can answer. I see them. Any other questions? So just out of curiosity, how many people knew that network function virtualization was really aimed at virtualizing network hardware? Few? And it's a really valuable thing for some entities. How many people looking at NFV and knowing it's designed to virtualize network hardware see an application for it in the way you work today? That's what I thought. It's a very focused solution set. And it's not necessarily what the enterprise is doing. The enterprise is really focused on SDN. And SDN solves the centralized control issues. Someday the enterprise may care about virtualizing the actual hardware itself, but the effort and the money to do that is definitely being driven by the people where the network is the business. And that's what's going on. That's what NFV is. That's what OPNFV is, or Open Platform NFV is. And this is the area that SUSE is working on. Any other questions? Okay, thanks.